Hello, everybody. Welcome to one more session at the JuliaCon. So let's welcome Dr. Rackauckas for the talk, Optimal Uncertainty Quantification of SciML model.
Yeah, thank you very much. So this has been a long-going collaboration with the Air Force Research Lab between MIT, Air Force Research Lab, and Julia Hub. We've been working with Adam Gerlach and his group for now like 4 or 5 years. It has really evolved into something which I think is very useful to a lot of applications. So what I want to describe today is what optimal uncertainty quantification is, the libraries that are being developed, what it kind of are doing, but also an idea of what they're useful for. So I'm going to start with like a really nice example problem that exemplifies what it's all about. So here's a picture, right? Imagine you have a seesaw and there's just a bunch of sand on the seesaw, right? There's some distribution of sand, right? But you know that the seesaw is balanced, right? And the question is, what is the maximum amount of sand that is to the far right of the seesaw? This is the question, right? So there's some possible distribution of sand. So any possible continuous function distribution, what is the maximum amount of sand over here? You think, oh, that's impossible, right? But we do actually have one piece of information. If the seesaw is balanced, then the forces on the left equals the forces on the right. So what can we do with that? Well, if the seesaw is, one thing that we could look for is what is the worst case scenario? Well, what is the way to get the most sand on this seesaw? Well, what we could do, right, is we could say, okay, there's some distribution of sand, but if I want to be able to get more sand on the seesaw, I can make it so that way it's pushing down on the left more, right? Because if there's more force over here, then I'll be able to put more stuff over here, right? And how can you get more of a force on the seesaw? What you can do is you can push it as far left as possible. So push all the sand to the left. And if you want to also make it so that way the force on the sand on the right is also, as low of a force, you push it towards the middle as much as possible. So there's this continuous distribution, but the worst case scenario, or the scenario where we can put the most sand on the seesaw, is where we put all of the sand over at 0 and all of the sand at the furthest point to the right where we're measuring from. And we say, how much sand can I put in that case? And that is the maximum amount of sand that I could put to the right of. For any possible distribution of the sand, that's the maximum amount that could be to the right of that point, right? Now, why is this a question that we'd be interested in? Well, it turns out that you can do a lot of worst case probabilities as this kind of problem, right? So for example, let's say we want to build a flood barrier and we want to be able to say what height for the flood barrier should we have such that there's a 99% chance of being safe. That turns into a problem of saying over all possible probability distributions that satisfy certain properties, how do I make it so that way every single probability distribution, there's only 1% chance that something can go wrong. And that's exactly the same problem, right? Where any possible distribution, I want to find the percentage of being in the bad portion. It's exactly the same problem. And now it's weird because it's like, oh, over all distributions, how is that solvable? But like what I described is that even though we're looking over all possible distributions, the worst case scenario can be described as, oh, you put sand in 2 parts, right? So it turns from this huge continuous problem into a discrete optimization problem. And it turns out that that's a general principle that you can prove. So you can show that finding the worst case distribution turns into a problem that you can do a discrete optimization. So here's the problem, right? We want to be able to find the probability that something happens, given that we know, the expected values and variances, and we want to be able to find this probability over the space of any possible distribution that satisfies those expected values and variances, right? So, why are we doing this, right? Why do we not just do Monte Carlo simulation? Well, if you do Monte Carlo simulation, you have to assume, oh, my parameter uncertainties have this distribution, and and you push things forward and you say, there's this percentage chance that something goes wrong, right? But that's not enough for safety critical applications. We want to be able to be certain, right, that if I say that the average wind speed is 3.5 and the variance in wind speed is 4, then I want to be able to say for certain that I know that for any possible probability distribution, there's less than a 1% chance that the plane will fall out of the sky, right? And this is exactly what optimal uncertainty quantification lets you do. So you could basically build this system in a modeling toolkit-like language, and what it'll do is it'll generate an optimization problem that is this discrete optimization problem that finds the worst-case scenario distribution and tells you whether the worst-case scenario satisfies these probabilistic constraints. And if you satisfy that, then you know that for all possible probability distributions, you are safe. And so what we're able to do is, for this is for the flood barrier problem, we're able to say, oh, if the barrier height is 2.0 meters, there's a 17% chance that that you can have a flood. But if you make the flood barrier 4.5, 4.6, there's a 0% chance that for any probability distribution that satisfies the mean and variance requirements that we put down, that it will be unsafe. And you go, okay, that stops flood. How can you also do this with dynamical systems? So what we've then also done is we made it so that way you can connect this to all the dynamical systems modeling, and then you can turn this, you can get these flow through the dynamical system models and apply the same optimal uncertainty quantification tool. And from this, then what you're able to do is be able to make statements like, if you only know the starting point of the plane, there's a 31% chance that the plane will hit a wall. But if I know the mean and I also know the variance of the wind, I could certify that there's a 0% chance for any possible probability distribution, right? No probability distribution has more than a 0% chance that it will cause an accident, right? And so this is something that you can actually then certify. We're able to do this with certified global optimizers. It is a very difficult numerical problem, but we've been scaling it and we're continuing to improve this. So you'll find this as OptimalUncertaintyQuantification.jl in the SciML repos, and this is something that we believe can change how people will do safety critical analyses in the future, given that it can certify, 4 uncertainties for every probability distribution, whether something is safe or not. So thank you very much.
Thank you for the talk. We have time for one quick question.
I wanted to ask about the guaranteed optimization results on dynamical systems. If there's something like, can we guarantee that optimization results on a dynamical system is in a certain...
Yeah, that's a great question. So it's a very difficult problem, right? Because the numerical solvers have their own error, and we want to make sure we account for that error. So what we're able to do is we're able to use reachability analysis tools and Taylor models to be able to bound the error that comes from the ODE solver, and then we're able to so that way that's taken into account, and so then we get a flow that includes the possible uncertainty quantification of the uncertainties of the parameters and the bound that includes the numerical tools, and be able to bound, given all of that together, does what you're trying to do, certify that the planes, the two planes will not collide given uncertainties in the wind, right? And so, yeah, we're able to take that all into account. That means that it is ridiculously computationally expensive. This is hard to do for very large systems. We call large systems in this space about like 10 variables, right? But we're working a lot on the scaling and the GPU aspects and such because it has this very strict property of guaranteeing safety. So.
Thank you so much. For the sake of time, let's thank Chris, and you can find him around and ask more questions.